Okay, this video we're going to look at infrared spectroscopy, or IR spectroscopy it's commonly called. Okay, so the range of the spectrum that we're looking at for infrared is from below our visible red to longer wavelengths up to 1 millimeter. Okay, and remember this low energy is not enough to change electron orbitals. So it's not enough to promote electrons to higher orbitals, and it results in, and if this was a GIF, these bending and stretches, okay, of chemical bonds. Okay, so only asymmetric bending or stretching absorbs in the IR, or the infrared. So diatomic molecules like O2, N2, Cl2 are not IR active. They won't absorb in there. So we need some asymmetric stretching here. So most organic molecules fit that criteria. So as bond energies are quantized, so are the bending and the stretching energies of certain molecules. Okay. So if a complete and even spectrum of IR energy, so you get a nice wide range of IR energy and you shoot it through your sample, certain sections of that will be absorbed, so you'll get less transmittance, okay, at certain wavelengths, and these are related to certain bond absorptions. Okay, so what you get is an IR spectrograph or spectrogram, and it looks just like this, where you have the y-axis as transmittance. Okay, so notice it's kind of like the baseline is 100% or just like a wiggling around 100%, and then you get these dips down where absorption is going on, and so transmittance is lower, and down the bottom you get like a scale of wavelength that is related to it. Okay, I think this is what I was just mentioning here. So it's a measure of absorbance over certain wavelengths. Y-axis is a percentage transmittance, so it's usually nice and high. It's a bit. This one isn't. Look at that. This one's a better example up here. Okay, so this scale on the x-axis that we call wavelength, that's the easiest way for us to remember it. But for some weird reason, I don't know why, it's given this other value called wave number. So some chemist scientists thought about this early on. It's inverse centimeters. Okay, horrible unit. Okay, what you need to remember is the higher the number, the smaller the wavelength. So relate it back to frequency if you will like. So larger numbers, higher frequency. Yeah, or you could think of it as the higher the number, the higher the energy. Okay, so usually we go from about 4,000 of these wave numbers to somewhere around 500. The higher the number, the higher the energy. Okay, so in this absorption here is a high energy absorption relating to some type of bending and stretching between two atoms or a bond in there. Okay, and here again is another peak that's related to some other stretching in the molecule, some separate different bonds. Okay, so the one that I showed you here, I'm not too sure what that one is, but this one here, I've got it in the title there that I stole. It's for ethanol. Okay, this one here looks like a carboxylic acid to me, and hopefully you'll get there. This one here, I guess, was an alcohol too. So what you're going to have a look at is absorbances at certain wave numbers, or absorbances at certain sections will tell you what's in the molecule. Okay, I should probably, the power of infrared spectroscopy is that you can see what functional groups are on your molecule. It can't give you a molecular formula, it can't always give you how it's joined up, but it can tell you what functional groups are there. That's the power of infrared spectroscopy. It has a lot of failures in the other ones, but it can tell you what functional group you have. Okay, and that's kind of what I'm going to show you here in two different ways. So down the bottom here, we've got, I like this, it's a graphical guide of what you can see in there. If you see this peak, it means you have this in your molecule. That's what it's saying. Now, over on the right-hand side is infrared absorption data. That's on your data sheet in the exam, okay? So, although this is a handy table to show it, this is what you'll be looking at in an exam to interpret your mass spectra. So, I put them kind of both in there. Now, with this one here, with ethanol, this box that I've put around in red is the big indicator, okay? So, this is this one here, the OH stretch, okay? The OH bond is stretching and it absorbs a nice wide band. That's what this is telling you. A nice wide, deep peak between 3200 and 4200 roughly. That's how you know you have an alcohol. So if you see that shape in there, you've got an alcohol. So when I look at that, I'm looking at it going, well, yeah, we've got an ethanol. Okay. So there's other things that you can see, like this kind of one in here is not too telling, but you'll see it in a lot of them, and you can see it around here as well. It's just it's the alkyne, it's the carbon-hydrogen bond stretch, okay? So you also get this other one's carbon-hydrogen stretches in here. Oh, hang on, that's not an alkyne because we don't have an alkyne. These ones here, yeah, they're the carbon-hydrogen stretches. If you have, a triple bond, you're going to get a peak in here. Oh, but why is that peak there? Anyway. And at the 1650 to 1800, you could get a deep carbonyl stretch, or C double bonded O, and that is what I'm seeing here in this one. But anyway, okay. So a good sign of an alcohol is you have this nice and broad peak between what they've listed here, 3230 to 3550, or let's just call it 32 to 36, okay? So you look at that, you see that peak, you're like, this is telling me I've got an alcohol. All right. So this other one in here that I've highlighted in red, not that handy at all. It's telling you you've got some CH stretches. I cannot imagine they're going to give you an organic molecule without some carbon-hydrogen bonds in there. So really, it's there. Ignore it. That's not telling you much at all, okay? Yeah. You could have an exam where they say, tell me all of them, and put the CHs in there, of course. All right. Now, this one up here, that's the carbon-oxygen bond there. And although it isn't on our graphical one here, it is here, 1000 to 1300. It's not a very deep one. We'll get to a very deep one here, but you can see it's a CO stretch. Okay? Can help you there. All right. Down here, I've got carbon to carbon stretches. Not very handy again because, most of our molecules have more than one carbon again. So that's not a big game changer that if you see that in there. Okay. So, IR spectra are very handy for beginner chemists to identify functional groups. Oh, now I'm talking about it. With oxygen atoms, so alcohols, aldehydes, ketones, carboxylic acids, and esters, okay? So we're really looking at how is the oxygen arranged here. They can be quite handy with amines sometimes too, but you'll notice on here, most of these things are some kind of oxygen in them, okay? So if you're looking and you see this wide peak up here, you're looking at an alcohol, okay? Where did I put the green in there? Because it's lacking a carbonyl, okay? It hasn't got a carbonyl in there. We've got an alcohol, okay? So here I've got the IR spectrum of 1, 2, 3, 4, 5, 6. So hexane and then hexane 1-ol. 1, 2, 3, 4, 5, 6. Yeah, hexane 1-ol. And you can see that the main difference between the two is this OH peak and this carbon. But it's got this carbon-oxygen bond there, this 10 to 13 one in there, okay? Oh, but why is it in that one? Oh, let's ignore that. Don't use it. But the big thing to see is you've got that nice broad peak, okay? Broad peak and no carbonyl there, okay? Because we'll get to where you've got a broad alcohol peak and a carbonyl, and that's a carboxylic acid. So we'll contrast it with that, okay? So when we look at these two areas, an alcohol just has that nice broad peak, okay? Okay, let's contrast it with a carboxylic acid. Here's my hexane 1-ol. You've got that nice broad peak. Here's hexanoic acid, okay? There's a few more little bits in here. Don't worry about that area. It's hard to define. What you're going to see is sometimes a more broader alcohol peak that drowns out those carbon-hydrogen stretches. And you'll see this really, really deep carbonyl stretch, C double bonded to O stretch, okay? So if you see these two in conjunction, you know you've got a carboxylic acid, okay? If you only see the OH stretch there with no carbonyl, you know that you've just got an alcohol. Okay. Ketones and aldehydes. All right, here is my alcohol, and here is either, I haven't got enough information to tell whether it's a ketone or an aldehyde, or I haven't got enough information to tell me if that's carbon double bonded to the oxygen is in the middle molecule or on the end. IR cannot give me that information, but it can tell me that there's a carbonyl, and you can see that in the green box here, and I've kept the red there. Notice that there's a lack of alcohol wide peak there. Okay, so it's not a carboxylic acid, but it's got a carbonyl on it because that deep carbonyl peak is there, but no alcohol peak. Okay, so it's not a carboxylic acid. Okay, esters. Esters give similar to aldehyde and ketones. They will not have a broad alcohol group peak. Okay. They will also have a pronounced absorption around the 1680 to 715. Okay, so let's have a look at that little words. Okay, so up the top here, I've got my carbonyl in green. And notice this new carbon-oxygen deep peak here. Okay, so the 1,300 peaks there. Okay, still in red, no alcohol group there. Okay. So the way to tell between my my ester and like my ketone or aldehyde is looking for this carbon-oxygen stretch, okay? And it's another deep one there. Notice it's there's still kind of a deep one there, but it's not as deep. Okay, that's the best we can do. Okay, so here's a couple more examples. Here I've got, I think it looks like it's carbonyl. Oh no, it's an ester. Okay, CH3CO2CH3. So it's a methyl ethanoate, isn't it? From that formula. But if you didn't know the formula, you'd see your carbonyl stretch and your carbon oxygen ones there. Okay. Cyanopentene. Oh, you know what? I don't think they're going to do those. Here I'm just trying to show you an example. Okay. I don't think they're going to go that one. Okay. What have I got? One from the textbook here. So, oh, heptane, methanol, and propanone. Okay, heptane, nice and simple, just those CH bends and CH stretches. Notice how with an alcohol now, we get that signature alcohol group. Yes, we've got that CO bond there. That's okay. That's the big teller. Here, we've got no alcohol, but we've got a carbonyl, so we've got an aldehyde or a ketone. Okay, that's as much as infrared's going to tell us though. Okay, we've reached its limit. Now, compound interest. Here's just a more detailed one. there if you're really, really interested, but I'd say stick to the simpler ones, okay? And you can do that worksheet. All right, so IR spectroscopy is just going to give us information on certain functional groups that are there. We're mainly concentrating on, is it an alcohol? Is it a carboxylic acid? Is it a ketone slash aldehyde? Okay, they're the main things that I want you to distinguish between. I think that's really all they're going to throw at us in an exam. All right, thanks guys. We'll call it quits there with IR spectroscopy.